Hi, in this video we are going to start implementing our linked list data structure. So let's get started. I'm going to create a distinct package for each data structure we are going to implement in the coming videos. So first of all, I'm going to create a package for our linked list. Okay. I'm going to create the PyDev modules. I'm going to have a node. It's going to denote the nodes of our linked list. I'm going to have a concrete linked list, and I'm going to have a class from which we are going to test our linked list data structure. So app, for example. Okay, let me start with the node. It's very important that, unlike Java, for example, or C#, Python do not support getters and setters. I mean, it is support, but there is no need for such methods. So I'm going to have a class node. It has an object. As usual, I'm going to define the constructor, the init method. It's going to have a self and a name. It's going to denote the name of our vertex or node in our linked list. It's going to store the data itself. So I'm going to have it's not a name, let me call it data, and it's much straightforward. That's why is it here. Self data is equal to data. And by the way, I'm going to have a pointer to the next node, which in this case is going to be none. It's a null in Java because there is no other node for which we are pointing at. And yes, we are going to have a method that's going to remove the items. So if we have a data to remove, and we have to store a reference to the previous node, and if the self.data is equal to the data we are looking for, that means that we are here. So we just have to set the previous node dot next node is equal to the self.next node. As we have talked about in the theoretical video, we just have to update the references, so these next node references, and we have to delete in order to avoid obsolete references and to be able to the garbage collection to do its work. So we just have to get rid of the references, the data, and we have to get rid of the next node. Okay. And else we have to check whether the next node is not none, so it's not a null pointer. We just have to solve the next node and have to call this remove method recursively. So data and self. Okay. Self.next node dot self. Not now. To self. What's the problem? I don't know. Self. Okay. Okay. So in our linked list class, it's going to be the class linked list with object. I'm going to import the from linked list package dot node class. Let me import the node class, and here we just have to set the constructor. It's very important that, unlike Java, we don't have private methods, I mean private field variables. We have to define in the constructor in the init method. So it's going to get a self, and here we have to specify that we are going to have a head. It's going to represent the first node in our linked list. First of all, we set it to none because there is no nodes in our linked list. And we have to define the insert method. So we can insert at start and we can insert at the end. It's very important that if we insert at the start, we can do it with constant time complexity. If we insert at the end, we have to traverse through the whole linked list, so it will have a linear time complexity. Insert at the end, so we have to specify a next node. It is equal to node.data. Oh, we have to specify, of course, we have a data we want to insert. And if not self.head, which means that the self.head is none, it is a null pointer. That means that it is the first element, so we set the head to a new node, to the new node. I rename it not next node, maybe new node is better. Okay, and else we know that we already have elements and items in our linked list, so we have to set the new node that next node is equal to self.head, and the self.head is equal to the new node. So we just keep updating the references. Okay, we are going to have a size method. Maybe it's very important to self.counter. It's equal to 0 at the beginning, and on every insertion we just have to increment this counter. Plus equals to 1. Oh, 1. So if we, in this situation, we don't have to traverse through the whole linked list. So we can do it with the help of constant time complexity instead of linear time complexity, when we have to iterate through the whole linked list and count each items in it. That counter, okay. That's the size. And let me specify, we are going to have a insert at the end method. We can do it with the help of linear time complexity, and that's why usually linked list relies heavily on insert at the start, because we can do it very fast, constant time complexity. Unlike inserting at the start, inserting at the end operates in linear time complexity, which is not so efficient, but it's not so bad. It could be quadratic, it could be ordo factorial, which is very bad. So linear time complexity is good in the main. Okay, so I'm going to have a new node. It is equal to the we're going to instantiate the data. We are going to have an actual node. It's going to have a self.head, and while the actual node dot next node is not none, means we keep iterating through, we keep hopping from node to node and keep checking whether the pointer points to a null or a none or not. And if it is while not, we keep iterating. So the actual node, of course, is equal to the actual node dot next node, of course. So it means that after this we are at the end of our linked list, and we just have to insert actual node that next node is equal to new node. We just insert the new data there. I think it's pretty straightforward. So as far as the remove method is concerned, remove, we have a data to remove, and if the self dot head, which means that the head is not a none, so we have elements in our linked list. If data is equal to the self.head.data, it means that it is the head of our linked list which we want to get rid of. We just have to self.head equals to the self.head.next node. We just keep updating the references. It's not so hard, I think. After writing it out several times, it will be easy. Okay. So else we know that it is not the head we are looking for, we want to get rid of. So we have to call the remove method. We have write, let me wait a second, is going to be the self.head. So this is the method with which we have implemented here. We keep iterating through the whole linked list and check whether it's a match or not. If not, we keep iterating through, and that's why the worst case scenario that the running time is linear. We keep iterating through the whole linked list. The list has n items, so we keep iterating through. If we are lucky, it can be sublinear. So for example, if it is the head, it's going to be order 1 constant time complexity because it is the first element we want to get rid of. But in the main, it's going to be linear. Okay, so in the app, we have to import from linked list import linked list. Okay. And I think the problem is class linked list. What's the problem? From the package linked list and the class linked list, we want to import linked list. What's the problem? Sometimes linked list is not so helpful. Anyways, I'm going to write it, and later on I'm going to solve this problem. So the linked list is equal to linked list. We just have to instantiate, and the linked list, and we keep inserting elements. For example, we insert 12. We keep inserting elements such as that. We keep inserting 3. We keep inserting 31, whatever. And we want to linked list dot traverse list. I think it is the method I am missing, yeah. So we just have to write this method. It's going to be linear. We have to keep running through the whole linked list. So traverse list. Okay, I'm going to define an actual node. It's going to point to the head, and while the actual node is not none, it means that it's not a null, so there are elements in our linked list. We just want to print out the content of our linked list, so it's going to be the actual node.data, and we want to hop to the other one, I mean the next node, .next node. Okay, so that's all about the traverse list method, and it has linear time complexity. As almost all the traverse algorithms, if you want to traverse a binary search tree, it's going to be linear. If you want to traverse a linked list, it's going to be linear. So it usually has linear time complexity. So linked list dot remove. We want to remove the 12, for example, and we want to traverse the list again. So if I want to run, I'm not sure whether there's an error. Python run, I usually like to run the app like this. Yeah, and there's an error message. It's not a package. From linked list node, I'm going to fix this problem. I'm going to be back. So I came to the conclusion that the Eclipse is usually doesn't like if the package name is the same as the classes you are going to import the classes. So I renamed the package to linked list data structure. That's why the DS. And it's working fine. I don't understand this kind of thing. It's kind of weird. That's why I use Linux, to be honest, because these obstacles are not valid there. So we have to insert, and I think that insert at the end. So let's test whether the insert at the end, we insert it at the end, we insert at the end, insert at the start, then traverse the list, then remove the 12, then traverse the list again. And I think that if we want to insert at the end, and it is the first case, and which means that the self.head is none, then we have to call the insert start method with the data and have to return, because if it's the first element, self.insert start, because if it's the first element, then we would get a null pointer exception, and otherwise here we have we saw that just the new node, if the self.head is null, then we instantiate it. So we just do the same, and we increment the counter here, self.counter plus equals to 1. And as far as the remove is concerned, we just self.counter minus equals to 1. So let's test whether it's working or not. And it's working fine, I think, because we keep inserting at the end. And we keep inserting the start, the 31. So 31, then 12, then 122, then 3. It's okay. It's the first traversal with this. Then we remove the 12. And yeah, that will be the order. So that's all about the linked list data structures. It's very important when we can get a linear time complexity or a constant time complexity. It's depending on whether we are inserting at the end, and if we inserting at the end, it will be linear time complexity, and if we insert the items at the start, it's going to be very, very fast with linear time complexity, and that's why we usually implement linked list in this manner in order to get the given time complexity. So thanks for watching. In the next video we are going to talk about binary search trees, I think. Thanks.